What if I told you that ghosts are real? Not the kind you're thinking of. Not something that goes through walls or haunts houses. I'm talking about something far stranger. Planets. Entire worlds, the size of Earth, the size of Saturn, drifting through the darkness between the stars alone, with no sun, no orbit, no home. Trillions of them. Right now, tonight. One of them may already be in our solar system, hiding, invisible, orbiting our sun for 4.5 billion years without us ever knowing it was there. Scientists call them free-floating planets. Some people call them rogue planets. I like the name ghost planets, because that's really what they are. Worlds that exist, that are real, that are out there right now, but that we can barely see and barely detect, moving through the darkness like they're not even there. And here's the thing that really stopped me when I first looked into this properly. There are trillions of them. Not thousands. Not millions. Trillions. The most recent scientific estimates suggest there could be roughly 20 rogue planets for every single star in the Milky Way. 20. And there are somewhere between 200 billion and 400 billion stars in our galaxy. You do the math. We're talking about a number so large it honestly breaks the imagination a little. And we have directly confirmed fewer than 30 of them. Fewer than 30 out of potentially trillions. Because they are dark. They don't shine. They don't reflect a star's light because they have no star. They are invisible in almost every sense of the word. And the only way we find them at all is through a rare gravitational accident that I'll explain in a bit. But here's where tonight really gets interesting. Because it's not just about those planets out there. It's about this planet, right here, the one you're on. Because there's a number, a real, verified, peer-reviewed scientific probability attached to the possibility that Earth itself eventually becomes one of them. 1 in 500. That's the published probability from a study released in 2025 that Earth is ejected from the solar system or destroyed in a planetary collision over the next 5 billion years. 1 in 500. Not zero. Not impossible. Not something that some fringe theorist made up. A number that came out of thousands of computer simulations run by 2 respected planetary scientists, published in the journal Icarus, supported by NASA. Tonight we're going to understand where ghost planets come from, why they exist in such extraordinary numbers, whether our solar system could ever capture one, and what would happen if it did. We're going to talk about the mathematics that proves the solar system's long-term future cannot be calculated. And we're going to follow Earth, step by step, through what it would actually become if it were ever flung into interstellar space. All of it is real science. Every number has a source. None of this is speculation. My dear curious friend, now it is your time to stay alone with curiosity. The planets that belong to no star. Let me tell you how we find these things. Because the method itself is one of the most beautiful pieces of detective work in all of science. Rogue planets don't shine. They don't orbit anything we can track. They produce almost no light of their own, just a faint infrared warmth from their formation, slowly cooling across billions of years. In terms of what we can see from Earth, they are essentially invisible, dark objects moving through a dark sky. The only way we find them is through something called gravitational microlensing. Here's how it works. Einstein showed us that massive objects bend light. They curve space-time, and that curvature bends the path of any light passing nearby. So if a rogue planet happens to drift between Earth and a distant background star, its gravity acts like a lens. It bends the star's light around it, and for a brief period, that star appears to brighten. Not because the star is doing anything, because there's an invisible world between us and it, bending its light toward us. The brightening lasts hours, sometimes days. It happens once, then it's gone. And from the shape of that brightness curve, how quickly it rises, how long it peaks, how it falls, astronomers can calculate the mass of the thing that caused it. That is how you find a planet you cannot see. You wait for it to accidentally stand between you and a star, and you measure the shadow of its gravity. The MOA survey, the microlensing observations and astrophysics project, has been doing this for years. They watch 50 million stars in the direction of the Milky Way center every night, looking for these brief brightenings. And from their data, they've estimated that there are nearly 2 Jupiter-mass rogue planets for every star in the galaxy. From 50 million stars and a handful of events, they can extrapolate the population of an entire galaxy. We have directly confirmed fewer than 30 individual rogue planets, out of what the statistics suggest are trillions. Think about that for a second. We know they're out there. We know roughly how many there are, and we have personally met fewer than 30 of them. For a long time, when we detected a rogue planet through microlensing, there was a frustrating limitation. We could tell it was there. We could estimate its mass, roughly, but we couldn't measure both its mass and its distance from Earth at the same time. There was always a mathematical ambiguity, a degeneracy, scientists call it, that meant you could explain the same observation with either a lighter planet closer to us or a heavier planet farther away. On the first day of 2025, that changed. A paper was published in the journal Science describing a rogue planet detected on May 3, 2024. The object had been spotted simultaneously by ground-based telescopes in Chile and Korea, and by the European Space Agency's Gaia satellite, which sits about 1.5 million kilometers from Earth, at a point in space called L2. Because Gaia was positioned slightly differently from Earth, it saw the same microlensing event arrive about 2 hours later. 2 hours. That tiny timing difference, caused by the slight difference in viewing angle from 1.5 million kilometers of separation, was enough for the team to triangulate both the distance and the mass of the planet at the same time. The result? A world about 9,950 light-years from Earth. Mass, roughly 70 Earth masses, comparable to Saturn. A real planet. Confirmed. Measured. Alone in the galaxy, nearly 10,000 light-years away. The co-author of the study, Subwa Dong of Peking University, said this: "Our discovery offers further evidence that the galaxy may be teeming with rogue planets." Teeming. That's the word a scientist chose. Not scattered. Not occasional. Teeming. And then, in October 2025, something even stranger. Astronomers published observations of a rogue planet called Cha 1107 to 7626, located 620 light-years from Earth in the constellation Chameleon. It has no star, and it is currently growing. Not slowly. By August 2025, it was accreting, pulling in surrounding material, at approximately 6 billion tons per second. The European Southern Observatory, which made the observation using the Very Large Telescope in Chile, described it as the strongest accretion episode ever recorded for a planetary mass object. The planet has its own disk of gas and dust around it. The James Webb Space Telescope confirmed the disk contains hydrocarbons and shows evidence of grain growth, the early stages of solid material forming within it. This disk could eventually form rocky companions. Moons, maybe. A miniature planetary system. Around a planet with no sun. The researchers put it beautifully. We are struck by quite how much the infancy of free-floating planetary mass objects resembles that of stars like the sun. A world in the dark, alone, building something, without any star to guide it. The universe is stranger and more prolific than we give it credit for. How a world becomes alone. So where do they all come from? How does a planet, a real world, something that formed in a disk around a star, something that had siblings and a sun and an orbit, end up alone in interstellar space. Let me take you back to the beginning, back to when a solar system is just forming. Imagine a vast cloud of gas and dust, slowly rotating, starting to collapse under its own gravity. At the center, a star is igniting, and in the disk surrounding it, something amazing is happening. Little bits of solid material are sticking together. Dust grains become pebbles. Pebbles become boulders. Boulders become planetesimals, rocky objects kilometers across. And over millions of years, through countless collisions, these planetesimals are building into planets. Now here's the thing nobody tells you about this process. It is incredibly chaotic. Dozens of these growing worlds are all in the same neighborhood, all gravitationally interacting with each other, all nudging each other's orbits. It's like a game of cosmic billiards where the table is never still and the balls never stop moving. Most of the players eventually find stable orbits. They settle. The game calms down. You end up with a nice, orderly system of planets. But not everyone gets a stable orbit. Some planets end up in the wrong place at the wrong time. They have a close encounter with a much larger planet, and in that encounter they lose. Here's what happens in that close encounter. When two planets pass near each other, their gravity pulls on each other. They exchange orbital energy. The bigger planet, because it's more massive, barely notices. But the smaller planet gets a significant kick. Depending on the geometry of the encounter, it can gain speed. A lot of speed. If it gains enough, it exceeds the escape velocity of the entire solar system. The star's gravity can't hold it anymore, and it just keeps going, outward, into interstellar space, never to return. A 2024 study of planetary formation in binary star systems, stars with two suns, found that each system ejected an average of between 2 and 7 planets during the formation process. Not occasionally, on average. Every system in those simulations threw away between 2 and 7 worlds. And that's just from the formation phase. The ejections don't stop there. They can happen at any point in a solar system's history. Whenever an orbit becomes unstable, whenever the gravitational balance of the system shifts enough to push a planet over the edge. You might be thinking, okay, but that was other solar systems. Not ours. Our solar system is stable and orderly, and has been for billions of years. And you'd be partly right, but only partly. About 3.9 billion years ago, something happened. The geological record on the Moon, and on Mars, and on Mercury, shows an intense spike in large impacts. Craters forming at a rate far higher than what came before or after. Scientists call this period the late heavy bombardment. Something disturbed the outer solar system, and the disturbed material rained inward, pounding the rocky planets. The leading explanation for what caused it is that the giant planets, Jupiter and Saturn, and possibly Uranus and Neptune, migrated significantly in their early history. Their orbits shifted, and as they shifted, they disturbed the material around them. Some went inward, some went outward, and some, almost certainly, left the solar system entirely. Some versions of the most detailed models of solar system formation require not 4 giant planets, but 5. A 5th world, comparable to Uranus or Neptune, that was ejected during the same period of giant planet migration that caused the late heavy bombardment. If those models are right, our solar system once had 9 planets, and the 9th was flung into interstellar space 3.9 billion years ago. It's out there right now, drifting, dark, alone, a world that was once our solar sibling, moving through the same space between stars that we're talking about tonight. A world that, had things gone slightly differently, could have been the one that stayed, and we could have been the one that left. Some versions of the most detailed models of solar system formation require not 4 giant planets, but 5. A fifth world, comparable to Uranus or Neptune, that was ejected during the same period of giant planet migration that caused a late heavy bombardment. If those models are right, our solar system once had 9 planets, and the 9th was flung into interstellar space 3.9 billion years ago. It's out there right now, drifting, dark, alone, a world that was once our solar sibling, moving through the same space between stars that we're talking about tonight. A world that, had things gone slightly differently, could have been the one that stayed, and we could have been the one that left. Born in darkness. Now I want to tell you about the other kind, because not all rogue planets were ejected from somewhere. Some of them were never part of the solar system at all. Some of them were born alone. Here's how that works. Stars form from the collapse of dense regions and molecular clouds. Vast, cold clouds of gas and dust that fill the spaces between stars. When a region gets dense enough, gravity takes over, and it collapses inward. The core heats up. Eventually, if there's enough mass, the temperature reaches 15 million degrees and hydrogen fusion ignites. A star is born. But molecular clouds don't collapse uniformly. They fragment. Different regions collapse at different rates, forming different-sized objects. Most form stars. Some form brown dwarfs, objects too small to sustain hydrogen fusion, but big enough to fuse deuterium briefly. And some form objects below, even that threshold, below about 13 Jupiter masses. Objects that never achieve any kind of fusion at all. These objects are just planets. Planetary mass objects, born directly from the collapse of a gas cloud, with no star nearby. They emerge from their natal cloud alone, cool down over millions of years, and drift into the galaxy as rogue planets that have never known a sun. In December 2021, astronomers detected at least 70 of these, possibly up to 170, in a single region between 2 star-forming areas in our galaxy. 70 rogue planets in one place, most of which probably formed directly from collapsing gas rather than being ejected from anywhere. And in October 2023, the James Webb Space Telescope found 540 planetary mass object candidates in the Orion Nebula alone. The universe doesn't just make planets as a byproduct of making stars. It makes them directly, on their own, in the dark. I know what you might be thinking. A world with no sun, no light, no warmth. How could anything live there? And that's a completely reasonable thing to wonder. But here's what's interesting. The assumption that life requires sunlight is actually a pretty parochial one. It's based entirely on our experience here on Earth's surface. But Earth's surface is not the only place life exists on Earth. In 1977, a research submersible called Alvin descended to the Galapagos Rift on the ocean floor. And what it found there changed biology forever. Entire ecosystems, flourishing in complete darkness, thousands of meters below the surface. Tube worms, chemosynthetic bacteria, crabs and shrimp. None of them had ever seen sunlight. None of them needed it. They were powered entirely by the chemical energy released from minerals venting out of the seafloor. Hydrogen sulfide, carbon compounds, heat from Earth's interior. That interior heat comes from radioactive decay. Uranium, thorium, potassium, isotopes embedded in Earth's mantle and crust, slowly releasing energy as they decay. It has nothing to do with the sun, and a rogue planet would have the same thing. The same radioactive heating, the same potential for geothermal activity, the same possibility of liquid water deep underground, around vents in total darkness. A University of Cambridge study published in 2023 modeled exactly this scenario. They found that under realistic conditions, moons orbiting rogue planets could maintain liquid water in their subsurface environments for between 1 and 10 billion years. 10 billion years. That's longer than the current age of the universe. So somewhere out there, right now, there may be a rogue planet with a moon. And on that moon, in the dark, underneath kilometers of ice, there may be a warm ocean. And in that ocean, around hydrothermal vents, something may be alive. Life that has never seen a star, that doesn't know stars exist, that has evolved in total isolation, sustained entirely by the heat of rocks, on a moon, orbiting a planet that belongs to nothing. I find that one of the most quietly extraordinary possibilities in all of science. Can our solar system capture one? Okay, so we've established that there are trillions of rogue planets out there, drifting through the galaxy. And our solar system is also drifting through the galaxy. So the question naturally arises, could we ever encounter one? Could a rogue planet drift close enough to our sun to be pulled in, to be captured? The answer is yes, in principle. And there's actually evidence in our own solar system that something like this may have already happened. In November 2003, a team of astronomers led by Michael Brown at Caltech discovered an object they named Sedna, after the Inuit goddess of the Arctic Ocean. And from the moment they found it, it was a problem. Sedna is about 1,000 kilometers across, roughly half the size of Pluto. Its surface is deep red, one of the reddest objects in the solar system, and its orbit is one of the most extreme ever measured for any solar system body. Sedna's closest approach to the Sun, its perihelion, is 76 astronomical units. To put that in context, Neptune, the outermost known planet, is at 30 astronomical units. So Sedna never gets closer to the Sun than 2.5 times Neptune's distance. Neptune's gravity cannot have placed it there. No known planet can. It's in a region of space that our models say should essentially be empty. So how did it get there? There are a few possibilities. One is that a passing star, early in the Sun's history when it was still part of a dense birth cluster, gravitationally perturbed objects into these extreme orbits. Another is that the influence of the hypothetical massive outer planet, the one people have been searching for, with orbits suggesting something large is out there beyond Neptune, nudged Sedna into its current path over billions of years. And a third possibility, one that serious scientists have genuinely proposed, is that Sedna wasn't formed in our solar system at all. That it was captured from a neighboring star during the period when the Sun was still young and its birth cluster was still intact, when stars were close enough together for planetary exchanges to occur. Michael Brown himself, who discovered Sedna, described it in 2006 as a fossil record of the earliest solar system. Whatever event shaped Sedna's orbit happened 4.5 billion years ago and hasn't repeated since. It's like a geological layer in a cliff face, a record of something ancient and violent, preserved in orbital mechanics. Sedna might be alien. Literally, a world that formed around a different star, was pulled loose in a gravitational encounter, and ended up orbiting our Sun, the most alien object in our solar system, and we found it by accident. Now, capturing a small object like Sedna is one thing. A world roughly the size of a large asteroid, on an extreme orbit far from the other planets, mostly harmless. But what if the rogue planet that got captured was massive? What if it was 5 times the mass of Earth? Or 10 times? What if it arrived on an eccentric orbit that crossed the paths of the existing planets, and kept crossing them on every pass around the Sun for millions of years? This is where things get genuinely complicated. Because a massive new body in the solar system doesn't just exist alongside the existing planets. It gravitationally interacts with all of them. Every pass is a perturbation, small on any given orbit, but accumulating over time. And the mathematics that governs what happens when you add new massive body to a system of existing ones. That mathematics has a deep, fundamental problem, a problem that has been known for over 300 years, and that has never been solved. The equation with no solution. I want to take you back to 1687. Isaac Newton has just published the Principia, one of the most important scientific works ever written. In it, he describes the laws of motion and the universal law of gravitation. He proves, mathematically, that the same force that pulls an apple from a tree is the force that keeps the moon in orbit and Earth circling the sun. And for two objects, just two, his equations are perfect. Give Newton the mass of a planet and a star, their initial positions and velocities, and he can tell you where the planet will be in 1,000,000 years. In 1,000,000,000 years. Exactly. No approximation. A clean, closed-form mathematical solution. Two bodies. Perfect. Now at a third. Suddenly, everything falls apart. The three-body problem. The question of how three gravitationally interacting objects move over time has no general closed-form solution. It never has. You can't write down a formula that, given any three masses with any starting positions and velocities, tells you exactly where all three will be at any future time. It doesn't exist. And this isn't because we haven't tried hard enough. The greatest mathematicians of the 18th and 19th centuries threw themselves at it. Euler, Lagrange, Laplace, Gauss. None of them found the general solution, because it isn't findable. That's the point. In 1887, King Oscar II of Sweden offered a prize to anyone who could prove the solar system was stable. Henri Poincaré, arguably the greatest mathematician of his era, entered the competition. He submitted a paper that appeared to prove stability, and he won the prize. But then, before the paper was published, he found a mistake. And as he corrected it, something deeply unsettling emerged. He found that the three-body problem, and by extension any multi-body gravitational system, was not just difficult to solve. It was chaotically sensitive to initial conditions, meaning tiny differences in starting positions or velocities, differences smaller than any measurement could ever detect, would eventually lead to completely different outcomes. Not gradually different, catastrophically different. The solutions diverged exponentially over time. Two configurations that started virtually identical would, after enough time, look nothing alike. This wasn't a computational limitation. It was a mathematical truth. The equations themselves contained irreducible unpredictability. No matter how precisely you measured the starting conditions, you couldn't predict the long-term future beyond a certain horizon. Poincaré had to publish a correction. He'd won a prize for proving stability, and the correction showed the opposite. The solar system's future, over long enough timescales, cannot be proven stable. It cannot be calculated. It is, in the mathematical sense, chaotic. What he discovered while trying to prove the solar system would last forever was chaos theory. Fast forward to 2009. Jacques Lasker and Mikhail Gastineau at the Paris Observatory run 2,500 computer simulations of the solar system's future over 5 billion years. Best available data, general relativity included. And then they do something small. They change Mercury's starting position by 1 millimeter. 1 millimeter. On a planet 77 million kilometers from the Sun. In about 1% of the new simulations, Mercury's orbit became so unstable that it crossed Venus's path. Mercury collided with Venus, or fell into the sun. And in some of those scenarios, the chain reaction propagated. Venus was disturbed, then Mars, then Earth. In at least one simulation, the entire inner solar system was destabilized. Earth was set on a trajectory toward ejection or collision. 1% probability from 1 millimeter. That tells you something very important about the solar system. It's not deeply stable. It's not robustly stable. It's marginally stable, balanced right near the edge of chaos, on the right side of it, for now, but not by a comfortable margin. Now, at a captured rogue planet. Massive, eccentric, crossing the paths of multiple existing planets on every orbit. That's not a 1 millimeter perturbation. That's a completely new gravitational player in an already barely stable system. And Poincaré proved what happens then. The future becomes unknowable, not hard to calculate, genuinely, mathematically unknowable. 1 in 500. Now I want to bring this close to home. Everything I've described so far, the chaos, the instability, the marginal balance of the solar system, all of that assumes no new arrivals. Just the solar system as it is, with the 8 planets it currently has, doing what they're currently doing. Even under those conditions, a study published in 2025 found something that I think deserves a lot more attention than it's gotten. Nathan Cabe from the Planetary Science Institute in Iowa and Sean Raymond from the University of Bordeaux in France published a paper in the journal Icarus. Their research was supported by NASA. They ran thousands of computer simulations of the solar system's future, covering the next 5 billion years, and they included something that most previous models had simply left out: passing stars. As the sun travels through the Milky Way, other stars pass near it, not close enough to feel dangerous on any human timescale. We're talking about encounters at distances measured in light years, happening over millions of years. But their gravity is real and cumulative. And over billions of years, those gravitational nudges on the outer solar system add up in ways that previous models hadn't fully accounted for. Cabe and Raymond found that on average, about 19 stars pass within about 3.26 light years of the sun every million years. Over 5 billion years, that's roughly 95,000 stellar passages, each one nudging the outer solar system slightly, each nudge feeding through to Neptune, then through the giant planets, then eventually into the dynamics of the inner system. Their findings were stark. Including stellar flybys reduced the solar system's long-term stability by 50 to 80% compared to isolated models. Mercury's probability of becoming unstable increased by 50 to 80%. The planets are significantly less stable than we thought. And for Earth specifically, a 0.2% probability of being ejected from the solar system or destroyed in a planetary collision over the next 5 billion years. 1 in 500. The mechanism is specific, and it's worth walking through because it shows exactly how something happening on the other side of the galaxy today could eventually affect us billions of years from now. It starts with Mercury. Of all the planets, Mercury has the most eccentric orbit already, the most elongated ellipse. And there's a specific gravitational resonance that can develop between Mercury's orbital precession and Jupiter's orbital precession over billions of years. If they fall into sync, Jupiter's repeated gravitational nudges on Mercury become systematically reinforcing rather than averaging out. Mercury's orbit slowly, over hundreds of millions of years, becomes more and more elongated. Eventually, Mercury's orbit starts crossing Venus's path. A close encounter follows. In some scenarios, Mercury falls into the Sun. In others, it hits Venus. Bad for Mercury and Venus. Probably fine for everyone else. But in the less likely, and yet mathematically modeled, scenarios, the disturbance propagates. Venus gets pushed. Mars gets pushed. Their new, slightly altered orbits interact differently with Earth. And in some of those simulations, the gravitational geometry works out in a very specific and unlucky way. Venus and Mars together redirect Earth outward, toward Jupiter. And Jupiter, 300 times Earth's mass, with one gravitational interaction, redirects Earth outward again, past escape velocity, into interstellar space. Earth becomes a rogue planet. Cabe himself said, "It's a little scary how vulnerable we may be to planetary chaos." A planetary scientist, using the word scary, 1 in 500. What Earth would become? Okay, let's follow it. Let's actually follow Earth through what would happen. The ejection itself would be gradual at first. Earth's orbit would become more eccentric over millions of years, stretching from the nearly circular path it holds today into a more elongated ellipse. Seasons would get more extreme. Climate would shift. But Earth would still be orbiting the Sun. The final ejection, the moment Earth's velocity exceeded the Sun's escape velocity, would come from a close encounter with one of the outer planets. A gravitational slingshot. Years, maybe decades, of a wild new trajectory. And then Earth would be on a hyperbolic path, outward, accelerating away from the Sun. And the Sun, for the first time in 4.5 billion years, would start to shrink. In the early decades after ejection, if there were humans watching, the change would be subtle. The Sun would be visible, but getting smaller, dimmer. Over years, it would shrink from a disk to a point of light, still the brightest thing in the sky, but no longer warm enough to matter. Temperatures would start falling, slowly at first. The oceans hold a lot of thermal energy and don't give it up easily. But the trend would be unmistakable. Ice sheets spreading from the poles, glaciers advancing, tropical regions cooling to temperate, then to cold, then to something that doesn't have a human word for it. Within about 5,000 years of ejection, the surface oceans would be frozen solid. The atmosphere would start to freeze too. Carbon dioxide, minus 78 degrees Celsius, it becomes dry ice. That happens first. Planes of frozen carbon dioxide forming on the surface. Then nitrogen, minus 196 degrees, would start to solidify. The sky, which we see as blue because of atmospheric scattering, would go black. Absolutely black. Because there'd be nothing left to scatter the light. Earth would be silent, airless, frozen to temperatures close to absolute zero at the surface. A dead world, drifting through interstellar space. Or would it be dead? Here's the thing that most people don't know about where Earth's internal heat comes from. It doesn't come from the Sun. It never did. Earth's internal heat, the heat that keeps the mantle partially molten, that drives plate tectonics, that powers volcanoes, comes from radioactive decay. Uranium-238, thorium-232, potassium-40, uranium-235. Isotopes embedded in the mantle and crust, slowly releasing energy as they decay. About 20 terawatts of heat, continuously, independent of whatever is happening on the surface or in the sky. That heat would continue after ejection. The radioactive isotopes don't care whether Earth is orbiting the Sun or drifting alone in interstellar space. They decay at the same rate regardless. The mantle stays partially molten. The outer core stays liquid. Geothermal activity continues for billions of years. And where there's geothermal heat, there can be liquid water. Deep underground, around hydrothermal vents on what used to be the ocean floor, now buried under kilometers of ice. The same kind of vents where, today, in our current oceans, entire ecosystems exist in complete darkness. Tube worms, chemosynthetic bacteria, shrimp, sustained by the chemical energy of minerals venting from Earth's interior, with no connection to the sun whatsoever. Those ecosystems don't need sunlight. They never did. They need heat and chemistry. And a rogue Earth would have both for a very long time. A 2023 study from the University of Cambridge modeled the thermal evolution of moons orbiting ejected rogue planets and found that liquid water could persist in subsurface environments for up to 10 billion years. 10 billion. The universe is only about 13.5 billion years old. So here's the possibility I want to leave you with. Earth, frozen at the surface, dark and airless, drifting between the stars, might still be alive. Kilometers underground, around vents in the dark. Something small and patient and ancient, surviving on chemistry and heat, unaware that the star that created its world is now just another faint point of light in a sky it can no longer see. The ghost planet, with life still inside it. What if one came here? We've talked about Earth being ejected from the solar system by internal dynamics, bypassing stars nudging Mercury into a resonance with Jupiter that slowly unravels the inner solar system. That's the probability we've been discussing, 1 in 500 over 5 billion years. But there's a separate and more dramatic scenario I want to walk through. What if a rogue planet entered our solar system from outside? What if one of the trillions of wandering worlds out there drifted close enough to our sun to be captured? The odds of this happening in any given period are very small. The galaxy is mostly empty space, and the probability of a rogue planet making a close enough approach to be captured is astronomically low on short timescales. But remember, we have 5 billion years to go, and there are trillions of these objects out there. So let's think through what would actually happen. Orbit by a gravitational interaction with one of the existing outer planets. Neptune, most likely, or Uranus. A three-body interaction where the rogue planet loses energy to the outer planet, slows down enough to fall into a bound orbit, and the outer planet gains that energy and moves slightly outward. The captured rogue planet would arrive on an extremely elongated elliptical orbit. At its farthest point from the sun, it might be hundreds of astronomical units out. At its closest, it might swing through the region where the known planets orbit. Every time it made that close pass, it would gravitationally interact with multiple planets. Every interaction would perturb something. Every perturbation would add to the chaos already inherent in the system. Here's what makes this so destabilizing. The solar system's current stability depends on the specific configuration of the 8 planets. Every planet's orbit is in a delicate gravitational relationship with every other planet. These relationships have been slowly settling into their current patterns over 4.5 billion years. It's not perfectly stable. We've established that. But it's close enough to stable that the planets stay in roughly their current positions for billions of years at a time. Add a new massive body on a wild eccentric orbit, and you've changed the gravitational landscape of the entire system. You've introduced a new variable into equations that are already chaotic. And the mathematics of chaotic systems, which Poincaré proved cannot be solved in general form, says that adding a new variable to a chaotic system produces a future that is genuinely incalculable. The new planet doesn't need to hit anything to cause catastrophe. It just needs to be there, massive, on an orbit that crosses the existing planet's paths, accumulating small gravitational interactions over millions of orbits. Like water slowly eroding stone, each individual drop does almost nothing. But given enough time, the canyon forms. Over millions of years, the perturbations would build. The giant planets' orbits would shift slightly. Those shifts would change their gravitational relationships with the inner planets. Mercury's delicate balance with Jupiter will be disrupted. The cascade we described earlier, Mercury, Venus, Mars, Earth would be triggered, but on a faster timescale than in the passing star scenario. Because now the perturbation isn't coming from a star light years away. It's coming from a planet inside the solar system itself. Now, before this feels too alarming, let me give you the number that provides genuine reassurance. The probability of a rogue planet being captured by our solar system in the next 1,000 years is approximately 1 in a trillion. 1 in a trillion. Not 1 in 500. 1 in a trillion. The solar system is an incredibly small target in the vastness of the galaxy. Rogue planets are moving very fast relative to us, and the geometry required for capture rather than simple passage is rare. On the timescale of a human lifetime, of a civilization, of recorded history, the probability of a rogue planet capture is so close to zero that it's not worth a single moment of concern. It's mentioned in scientific literature, essentially, as a theoretical possibility rather than a practical risk. I'm telling you about it not because it's a danger, but because it's a window into understanding the fragility of the system we live in. The solar system is not a fortress. It is an open structure in a galaxy full of drifting objects. It has maintained its current configuration for 4.5 billion years not because it's impervious to disruption, but because disruptions large enough to matter are rare on the timescales relevant to us. We are lucky. We have been lucky for a very long time, and understanding that luck is not the same as being threatened by it. The long journey into the dark. Let me extend the story of what Earth would actually experience as a rogue planet, because I think we moved through it a bit quickly before. This deserves time. We established that the surface would freeze within about 5,000 years of ejection, that the atmosphere would eventually snow out, that the surface would be airless and cold to near absolute zero. But the interior would remain warm, driven by radioactive decay, for billions of years. And deep underground, liquid water and geothermal activity might persist for a very long time. But let's follow the whole journey. Let's think about what Earth's existence as a rogue planet would actually look like across the timescales involved. In the first million years after ejection, Earth would look, from space, almost exactly like the rogue planets we've been describing. A frozen world, a sphere of ice and frozen atmosphere, drifting in the dark. The Sun, the star it had orbited for 4.5 billion years, would now be just another point of light in the sky, indistinguishable from the other stars if you didn't know where to look. The surface temperature would have stabilized at somewhere around minus 240 degrees Celsius. The frozen oceans, kilometers of ice, would be among the most stable geological features on the planet, barely changing, barely eroding, because there's no atmosphere to drive erosion and no liquid water to carve channels or dissolve rock. But a kilometer down, or 2 kilometers, or 5, depending on the local geology, the temperature would rise. Geothermal gradients don't disappear overnight. The heat flowing up from the mantle would keep the deep subsurface warm. Not warm enough for humans, but warm enough for the kind of microbial life that thrives in Earth's current deep ocean vents. Those ecosystems, if they survive the transition, and there's no obvious reason they wouldn't, would continue. Exactly as they do now. Chemical energy from minerals. Warmth from radioactive decay. Liquid water in isolated pockets deep beneath the ice. Life in the dark, doing what life in the dark has always done. Over the first billion years of its journey through interstellar space, Earth would drift perhaps 1,000 to 10,000 light-years from the Sun, depending on the velocity it was flung out at. It would pass through regions of the galaxy it has never seen. The galactic center, with its dense concentration of stars and the supermassive black hole Sagittarius A* at its heart, would be visible from the frozen surface as a brilliant band of light, brighter than anything currently visible through Earth's atmosphere, because there would be no atmosphere left to absorb or scatter it. The stars would appear fixed. No seasons, no day-night cycle, because without a sun to orbit, Earth wouldn't be rotating through any meaningful light-dark boundary. It would simply spin, slowly, in the dark, with every point on its surface equally dark on every rotation. The stars would move slowly across the sky as Earth turned, but none of them would be close enough to warm the surface by even a fraction of a degree. Underground, the radioactive isotopes would continue their slow decay. After 1 billion years, roughly a third of the uranium-238 would still be undecayed. Its half-life is 4.5 billion years, the same as the current age of Earth. The heat production would drop slightly, but not dramatically. The mantle would remain warm. The outer core would likely remain liquid. Geothermal activity would continue, though perhaps at a slightly reduced rate. If life survived the first million years, it would very likely survive the first billion years. It would have adapted. It would have had to adapt, though the pressures driving adaptation would be different from anything life on the surface of a sunlit world experiences. But life is adaptable. The organisms living in Earth's deep ocean vents today are among the most ancient lineages on the planet. They have survived ice ages, mass extinctions, asteroid impacts. They are built for endurance. After 10 billion years, which is longer than the current age of the universe, Earth's radioactive heat production would be significantly reduced. The shorter-lived isotopes would be largely exhausted. The heat flow from the mantle would have dropped considerably from its current level. At some point in this timeline, the outer core would solidify. The magnetic field would cease. The last of the geothermal vents would go cold. The last liquid water would freeze. And then Earth would be truly, finally, completely frozen. A dark ball of rock and ice, drifting through the galaxy, carrying the preserved record of everything that ever lived on it. Fossils compressed in rock layers, proteins frozen into the ice, the molecular signatures of 3.7 billion years of biological history, preserved in the cold. A rogue planet with a geological and biological record unlike anything else in the galaxy. A museum drifting in the dark with no visitors. Unless, and this is the one that gets me, unless billions of years from now, some other civilization on some other world, with instruments more powerful than anything we can currently imagine, detects a faint infrared signature from a cold, dark world drifting through their region of the galaxy, and send a probe, and find the fossils, and the frozen oceans, and the remnants of the deep sea vent ecosystems, and understands from the chemistry and the geology and the biology that this world was once alive. They would know we existed. They would have no idea what we were. They would have found us entirely by accident, in the dark, billions of years after we were gone. I find that simultaneously one of the most melancholy and one of the most beautiful possibilities I can imagine. What Planet 9 was like as a ghost. I want to take you somewhere specific now. I want to take you to Planet 9, not as it is today, half captured in an extreme solar orbit, but as it was before, when it was a true ghost planet, drifting free, belonging to nothing. This requires some imagination, because we're describing something that either happened or didn't billions of years ago. But the physics is real, and it paints a picture that I think is worth spending time with. Imagine Planet 9, or whatever world became Planet 9, shortly after it was ejected from its original solar system, or shortly after it condensed from a molecular cloud as a born-free rogue. Either way, the moment it left its last gravitational anchor, it became what astronomers call a free-floating planet. The experience of being a rogue planet is, in physical terms, absolute isolation. There is no sun. There is no orbital period. There is no day and night in any meaningful sense. The planet rotates, and one hemisphere faces whatever direction it happens to face. But there is no single bright object to define the distinction between light and dark. All directions are equally dark, except for the faint general glow of stars in all directions. The temperature at the surface would depend on the planet's mass and age. A massive gas, giant rogue, still warm from formation, might have surface clouds warmed to a few hundred Kelvin by internal heat for millions of years. A smaller, rocky planet would cool faster, its surface dropping toward the cosmic background temperature of about 2.7 Kelvin, barely above absolute zero, within millions of years of its ejection. Planet 9, at 4 to 10 Earth masses, is in between. It's likely a mini Neptune, a rocky core surrounded by a thick hydrogen-helium atmosphere. In its first millions of years of freedom, its interior heat from formation would keep it warm enough to have active weather in its atmosphere, convective currents, perhaps a magnetic field generated by its conducting metallic interior. Over tens and hundreds of millions of years, it would cool. The atmosphere would settle. The weather would calm. The interior would slowly solidify. But the cooling would take a long time. A world of that mass carries enormous thermal energy from its formation, and the radioactive isotopes embedded in its rocky core, uranium, thorium, potassium, would provide a slow, steady source of internal heat for billions of years, independent of any star. As a rogue planet, Planet 9 would have been subject to the galaxy's overall gravitational field. The combined gravity of hundreds of billions of stars, dark matter, and the interstellar medium, all pulling in different directions as the planet moved through different parts of the galaxy. Over millions of years, this galactic gravitational field would gently curve the planet's trajectory, nudging it in ways that accumulated over vast timescales. A rogue planet is not truly free. Nothing in the galaxy is truly free of gravity, but its gravitational master is the galaxy as a whole, not any individual star. How long did Planet 9 drift before our sun caught it? We don't know. It could have been millions of years. If it was ejected from a nearby system in the birth cluster and the sun caught it quickly, or it could have been hundreds of millions of years if it drifted for a long time before the encounter. Or it could have been born free in the birth cluster and never had a star to be ejected from, making the sun the first gravitational home it ever had. The duration of the drift would be written, at least partially, in Planet 9's thermal history. A world that drifted for only a few million years would still be warm from formation when it was captured. A world that drifted for hundreds of millions of years would have cooled significantly. The internal temperature profile, if we could ever measure it, would give us a clock. The capture itself, if it happened, would have been the most dramatic event in Planet 9's history. A world that had been drifting in complete gravitational freedom, subject to nothing but the galaxy's diffuse overall pull, suddenly encountering a strong gravitational field. A young star, bright and warm by the standards of interstellar space, pulling at the planet as it drifted near. The approach would have been gradual. From far away, the sun would have been just another point of light, brighter than most, perhaps, but not dramatically so. As Planet 9 drifted closer, the sun's gravitational pull would have strengthened. Planet 9 would have begun to accelerate toward it. The trajectory would have curved. Then the swing through. Planet 9 moving faster and faster as it fell toward the sun, crossing the orbits of the outer planets, perhaps interacting gravitationally with one of them in the three-body encounter that dissipated enough energy for capture. The young protoplanetary disk, if it was still present, providing aerodynamic drag as Planet 9 swept through it. And then, not a dramatic moment, not something that would have been observable from the outside as a discrete event, the transition, Planet 9's trajectory, which had been hyperbolic, becoming elliptical, the escape velocity of the Sun becoming greater than Planet 9's current velocity, the planet now in orbit, bound, no longer free. It would have continued outward, still moving fast, reaching its new aphelion, the farthest point of its new orbit, and then slowly, over thousands of years, beginning to fall back in, and then out again, and then again. The new orbit, eccentric and extreme, but stable, permanent. The ghost planet had found a home, and then the birth's cluster dispersed. The stars that had been neighbors moved apart. The conditions that made capture possible were gone forever. Planet 9's orbit slowly settled under the influence of the existing planets and the Sun's gravity. And the solar system, from that point on, looked roughly as it does now. 8 planets in the inner region, Planet 9 in the extreme outer darkness, until 2 astronomers noticed an anomaly in the orbits of distant icy objects in 2014. So let me pull all of this together. There are billions to trillions of rogue planets in the Milky Way right now. Most of them were ejected from solar systems during the chaotic early phase of planetary formation. Worlds that had homes and lost them. Some were born alone, from gas clouds too small to become stars, and have never known a sun. Some might even have been exchanged between solar systems, captured by one star, released, captured by another. The first rogue planet with a confirmed mass and distance was measured on the first day of 2025. A Saturn mass world, alone, nearly 10,000 light-years away. Another rogue planet, 600 light-years away, is currently accreting 6 billion tons of material per second, building a disk around itself, behaving like a newborn star. Alone in the dark. The mathematics of gravitational systems, 3 or more bodies interacting, has no general solution. Henri Poincaré proved in 1890 that these systems are chaotic, that tiny differences in starting conditions lead to completely different outcomes over time, that the solar system's future beyond a few tens of millions of years is, in a strict mathematical sense, incalculable. And the 2025 research by Cabe and Raymond showed that the probability of Earth being ejected from the solar system or destroyed in a planetary collision over the next 5 billion years is 0.2%. 1 in 500. Higher than any previous model had found, because previous models had ignored the gravity of passing stars. That number is not frightening on any human timescale. 5 billion years is a completely abstract span of time. The Sun will have already ended its main sequence life. Nothing about this is relevant to anything we need to do or think about today. But I think it matters anyway, because it changes something about how you understand the place you're sitting in. We are on the planet that stayed, that found its orbit and held it for 4.5 billion years through the late heavy bombardment, through ice ages, through mass extinctions, through all of it, held its orbit and kept its oceans liquid and kept its atmosphere intact and produced, eventually, life complex enough to understand what a rogue planet is. And right now, tonight, as you rest, there are trillions of other worlds that didn't stay, that were flung into the dark, some of them billions of years ago, some of them carrying moons. Some of those moons with oceans. Some of those oceans, possibly, with something alive in them. None of them know we're here. And we only know they're there because a handful of astronomers have been staring at 50 million stars, night after night, waiting for a 40-minute brightening that might mean something invisible just passed by. The universe is dark. It is vast, and it is absolutely, extraordinarily full. 1 in 500. Tonight, we're the ones who stayed. Rest well.